For this problem, we're going to work on an equilibrium problem. It has two parts, A and B. We will work on A first and then we'll work on B. And it's not all going to fit on this page, so I will start moving it up and adding a page on top of the data that's worked. So we're going to go ahead and work A right here. We're told that a given temperature, a 1 liter flask contains an equilibrium mixture composed of 0.68 moles sulfur trioxide, nitrogen monoxide, etc. So basically, what we're given in A is we are given the equilibrium concentrations. So all we have to do is look at them. Now, SO3 is the first one that's given. So SO3, remember, concentrations have to be in molarity. So we need to take our moles, which is 0.68 moles, divided by the volume, which happens to be 1 liter. So this comes out to be 0.68 molar. The second one is nitrogen monoxide, which is 0.82 moles per 1 liter, which is 0.82 molar. So 2 is 0.59 moles of sulfur dioxide over 1 liter is 0.59 molar. And last but certainly not least is nitrogen dioxide, which is 0.47 moles per 1 liter. Now remember, because these are all 1 liter, the moles is the same as the molarity. But if you were using 2 liters, then that would change all of them. They would not be the given value. So this is going to be 0.47 molar. Now, we know that these are the equilibrium concentrations because we were told. We want the equilibrium constant. So K, equilibrium constant, remember, is products, SO2 times NO2 divided by SO3 divided by NO. Okay, remember order of operation. So what we're going to do is substitute in what we have. So SO2 is 0.59 molar. NO2 is 0.47 molar. SO2 is 0.68 molar. And NO is 0.82 molar. Now, we run the numbers, and K should be equal to 0.4973099. Now, for simplicity's sake, since we're working the problem to learn how to work it, we're just going to use K is equal to 0.50. So A's done. So because I'm going to end up covering up my work, I'm going to go back up here and say K is equal to 0.50. Now remember, K has no unit values associated with it, so we don't have to put anything. So now I'm going to work part B here. And in part B, we are told that we're restarting the reaction vessel with initial amounts, and we want to know the concentration of all the species present. Well, if we know we're shifting it, then basically we need an ICE table. So in order to use an ICE table, I need an equation. So I'm going to quickly rewrite my equation here. And I know that my K is given. I'm going to leave that right there. We're going to start initially ICE. Remember, initial change in equilibrium. We're told that the reaction vessel initially contains 1.2 molar of the sulfur trioxide and 2.0 molar of the nitrogen monoxide. Since nothing was told about sulfur dioxide and nitrogen dioxide, we assume they're 0. Now, we know that the shift will go to the product side because there's a 0 there. The shift, if you have a 0 initially, there will always be a shift to replace that with something else. even if it's a pure solid, because pure solids have an activity value of 1, but you can't use a 0. Because we're going to shift to the product, and our coefficient is 1, we're going to lose x here, gain x here, and gain x here. So the equilibrium value is 1.2 minus x, 2.0 minus x, and x. So our K expression is still the same. It's SO2 times NO2 divided by SO3 times NO. Alright, so let's plug in what we know. We know this is 0.50. We know that SO2 is x, NO2 is x. The values here are 1.2 minus x times 2.0 minus x. So there we go. So here's where the fun begins, and by fun I mean algebra. So we end up with 0.50 is equal to, well, x times x is x squared. Now below we've got two binomials, so we'll have to use the FOIL method. So we're going to end up with 2.4 minus 3.2x plus x squared. Again, is still equal to k. Doesn't matter what side you put that on. But remember, when you FOIL, you take the first, outer, inner, and then last. Okay, so once we've done that, then what we're going to do is end up distributing, which means we're going to take 0.50 times 2.4 minus 3.2x plus x squared is equal to x squared, which comes out to be equal to 1.2 minus 1.6x plus 0.5x squared equals x squared. In order to solve the Pauli function, we have to set it equal to 0. So what we end up with is, the easiest thing is move everything to the right. You can do it either way you want, but I ended up with 0.5x squared plus 1.6x minus 1.2 is equal to 0. Now, this is where you put into the calculator. Okay? So when you do that, you're going to get two x values, but the one you're going to choose is 0.6271 molar, which, again, because we're working the problem, that means that x comes out equal to 0.63 molar. Now there are two ways to work this. The easiest thing is go back up to the equilibrium, and we know that SO2 is equal to NO2, which are both equal to x, which we know x is 0.63 molar. We want SO3, which we know was 1.2 minus 0.63 molar, which is equal to 0.573 molar. NO was 2.0 minus 0.63 molar, which is equal to 1.373 molar. Okay. Now, as a double check, you can take these values and say 0.63 squared divided by 0.573 times 1.373, and this will give you, should give you your K back, which is 0.5, and it does. So therefore, you've checked the problem, so you know you're correct. Now it's going to vary slightly, but it'll be the same value. So this is how you work a relatively simple equilibrium problem.